computer engineering, where he holds the Canada Research Chair in Nanotechnology. He serves as Vice President of Research at the University of Toronto and has spent sabbaticals at MIT, UCLA, Berkeley, and Harvard. He also founded and served as the CTO of Envisage Technologies. And as you all know, his work is the very inspiration for this year's conference, and we can't wait to hear about the dance of molecules happening in his lab. So I'll pass it off to you, Ted.
Great, it's wonderful to be here. Thanks for pulling together such a great event. So I'm going to talk about how nanotechnology is being applied by us and by other groups in addressing some of the most urgent problems related to sustainable energy. So I'll just start off with the energy itself. We use 18 terawatt years per year. That's equivalent to 7,000 full charges of your iPhone per day per person. It's a lot of energy. And as you look at the split of where we utilize our energy, certainly some is in the form of electricity. And so that's the kind of southeast part of this square. You can see that for commercial purposes and for residential purposes, and to a lesser extent for industry, we use quite a bit of electricity. And the reason I'm breaking this into electricity versus not, and looking at the total energy and CO2 footprint, is that the portion that's related to electricity, you can decarbonize by decarbonizing the electricity. And so progress in solar and beyond, and in wind and in hydro is serving the function of decarbonizing this portion of our total carbon footprint. But the larger portion, the northwest portion of my plot, almost all of transportation today and a major portion of industrial applications like chemicals and refining, these have carbon footprints that are not directly traceable to the electricity itself. And so unless you figure out some kind of chemical strategy towards energy utilization and storage, it's not as obvious how to decarbonize. You have to go through some kind of chemical route, like a fuel or a chemical feedstock, to decarbonize these major contributors to our global carbon footprint. Now, the good news is that there is a lot of renewable energy available. I'll start by just looking here at the kind of representation through the volume of these cubes, a representation of the total energy available. These little cubes, like the black one for coal, and the purple one for oil, represent the total integrated energy available on Earth. So it's stored. This isn't some kind of per year number. This is the total amount of proven reserves. Now, my big yellow cube is the total amount of solar energy captured by the Earth at ground level. So it's made it through the atmosphere, and is the amount that makes it every year. So I'm actually comparing apples and oranges here. My solar amount of energy is actually a per year number. Everything else is an integral over the time over which the Earth has been storing this through photosynthesis. So this is fantastic news. We have a huge amount of free renewable energy, and it's a question of figuring out how we capture it. And I'll also be talking about the need to move it around in space and time, which is to say storage and transmission. And the other bit of good news for the field of utilizing renewable energy is that its price has come down. This is a classic learning curve. The horizontal axis is a log scale, so you'll see cumulative shipments of solar panels, modules. And on the vertical axis, you'll see the module price also on a log scale. And you'll see that it's been orders of magnitude decrease in cost as we've spent orders of magnitude of increased scaling up, learning about the efficient and cost-effective manufacture of silicon. And this red line, which we've actually now crossed, is approximate grid parity. So it's the cost of solar cells that allow you to produce solar electricity at a cost comparable to what we can get from traditional fossil sources. In fact, there have been some very sensational announcements, especially in parts of the world that do have excellent insulation, about how cheap solar electricity can be. So this is a recent record from Abu Dhabi from this summer, where 1.3 cents per kilowatt hour solar electricity was producible through a business bid, an economic bid, to produce it. So this is a testament, of course, to the rapid reduction, the continuing and rapid reduction in solar electricity, solar module cost, and also the fact this is a good environment in which to produce this kind of electricity because it's abundant. The insulation is very high. So as penetration continues, so as we continue to try to meet more and more of our electricity needs through lower and lower cost electricity, of course, lowering the cost helps. You can see these projections from the U.S. Department of Energy for the blue, which is what fraction of U.S. electricity will become solar derived if we reach 6 cents, and what fraction will be solar derived if we meet 3 cents. But you can see those are only penetrations to 20 or 30%. And to penetrate further beyond that, there's a need to incorporate storage as well. To put it positively, once we do have low-cost storage, we can enable a much more dramatic penetration of our total electricity use from renewables. And the reason for this point is the intermittency of solar energy. And in general, there's an intermittent quality to wind as well. They may not have the same exact time cycles, but they also are intermittent. And so just to illustrate this on the scale of a day, our demand for electricity peaks in the morning when we're cooking our omelets, and in the evening when we're starting our dishwashers, and it's actually low during midday, and yet midday is when the sun is at its peak. And you can take this sort of pattern of a mismatch between supply and demand, and you can apply it to our annual cycles as well. Think of Canada, where we've got more sun in the summer, and we've got a lot of energy need inside the winter. So there's even a need to move energy around, not just on the diurnal scale, the day scale, but to move it around on the half-year scale, the seasonal scale. And the problem that occurs, and this is sort of what I was talking about 2 slides ago, but it's phrased a little more clearly here, is that when you model out increasing solar PV penetration, there are fewer times of day available when you're actually meeting an unmet demand with your renewable electricity. And so the problem here is that the value, so the willingness to pay on the vertical axis by customers for these intermittent renewable electricities goes down and down as you increase penetration in the grid. So one way to put this is that without storage of energy, solar is purely a price taker, i.e., if you're a solar producer, you need to take the instantaneous price that a customer is willing to pay. And a lot of the time, that's not a very high price because they have a lot of other options. So you solve that if you can store energy, and the more you can store it on different time scales and play it back on different time scales, and the more you can do it on very large scales in a very scalable and cost-effective way, the more you can address increasingly the need and the desire to incorporate renewable electricity into a larger and larger portion of our economic activity, and therefore to have greater and greater impact on our total CO2 footprint. So the way in which we and other groups conceptualize doing this is initially by taking carbon dioxide, which is now, instead of just thinking of it as a liability, let's start to think of it as a chemical feedstock for our processes. We're going to take carbon dioxide, such as from industrial flues, perhaps from a steel plant or a cement plant. We'll take water and renewables. These two are ingredients, so you can think of them as chemical feedstocks. You can think of the electrons, the reducing equivalents that we get from our solar or wind as part of our chemical inputs to this process. And then in an electrolyzer, and that's where I'm going to spend much of my time today, in an electrolyzer, this is a device also can be thought of as a system for catalysis, for electrocatalysis, that can electrochemically reduce the CO2. So essentially it can strip off the oxygens and can turn it into something more carbon and hydrogen rich. So it can turn it into hydrocarbons. Where traditionally, we often just use the word hydrocarbons and we think fossil fuel or fossil chemical. But in fact, hydrocarbons is just the chemical description of these chemically upgraded, so they contain more energy, forms of carbon compared to the more oxidized forms, ultimately the bottom of which is the CO2. So essentially we're upgrading, we're adding energy, we're moving up on the energy scale, our carbons, to promote them into these more reduced forms. And so we're storing energy. Now, if we put this into the chemical sector, such as the material science sector, if we make something like ethylene, that can go to making polyethylene, that can go into plastics that are going to be used for materials like car seats or carpets or furniture. And so we're sequestering the CO2 into materials. If we go instead to the right, we go into what we call the fuels loop. And so if we synthesize, say, ethanol, ethanol is a drop-in replacement fuel already. When you go to the gas station, you'll be putting a bit of ethanol in your car typically. So when we drop that in, we're placing a fuel that has been synthesized by consuming as much CO2 as it will ultimately emit upon combustion. So we're at least on a pathway towards net neutral or carbon neutral fuels when we consume CO2 that would otherwise have been emitted from the industrial plant, and we utilize it to synthesize the fuel. We store and then we utilize in whatever applications we use it in, for example, in transportation. And then here, in the short run, while the globe still has lots of industrial plant emissions, we can kind of cancel out the emissions from this truck by the avoidance of emissions from this flue stack. When we make further progress and we no longer have these point sources, we need to figure out how to capture CO2 on board from this truck or to capture it from the air. So that's known as direct air capture. I'm not talking about it too much today. It's a very interesting topic. And it's going to be part of the long-term pathway towards actually taking CO2 out of the atmosphere. But for the moment, we've got a lot of sources that are more concentrated and a little bit more accessible for our CO2. So I mentioned that this process, the CO2 reduction reaction, takes electricity, and in fact, it can be from any source, but for this to be interesting from a carbon perspective, it should be low carbon electricity or renewable electricity, combined with water and CO2 into the CO2 electrolyzer, and we synthesize something more economically valuable than CO2 and more energetically rich than the CO2. So what are our options for that more energetically rich product? Well, I did talk about ethylene. Ethylene accounts for accountable percent, 1 or 2% of total CO2 emissions. If you look at going from fossil-derived products to ethylene, to purified ethylene, to polyethylene, to materials, there's a couple of percent of global CO2 emissions there. So it's a very big one. It is a global commodity, which is to say its price is relatively low. It's about $1,000 per ton. But our modeling and that of other groups both show that if we reach very impressive performance from CO2 reduction electrolyzers, that we can produce it for about maybe 10 or 15% less than the current market price. So you see this gap in production cost and market price. That's a favorable gap. That means that we've got the opportunity to earn some money, and it's some money to be earned on a couple $100 billion global industry. So even one of these industries, the energy industry is about a $5 trillion industry today. The bigger amongst these sectors, such as the ethylene or the ethanol or the ethylene glycol or propanol, they're industries that are measured in the tens of billions and in some cases in the hundreds of billions, because they represent a few percent of this global $5 trillion market. So these are big businesses that we can potentially impact and renewably disrupt. Propanol is one. It's not quite as large an industry, but you can see that we can potentially have a greater price advantage. So where we have these larger gaps in terms of the price to produce and the market value, the markets may be smaller, but they're still pretty big. They're measured in the billions and the tens of billions. They might be good entry points into the field of renewable fuels and renewable chemicals because of these more favorable price gaps. So in terms of overall progress in this field, and I'm going to dive in on some of the ways in which this progress has been achieved, but in terms of the overall roadmap of progress, maybe 3, 4, 5 years ago when our group started to enter into this field, these metrics that I'll say a bit about were quite low. They were quite far from where we need to be. This is kind of an update as to where they are relative to where we'd like them to be. So for ethylene, for example, and looking at the Faraday efficiency, which is the fraction of electrons that we utilize in our system that go towards producing our desired product, we've now reached about an 80% efficiency. Our target is still higher than that, though. We wish to reach about 95% use of electrons that goes towards our desired chemical products. The energy efficiency, so this is essentially the chemical value of the product that we produce divided by the energy cost that we consume today. The energy efficiency has progressed to about 20%, but needs to get to about 60%. So there's actually quite a gap still, and quite a big opportunity for students and postdocs and professors working in the field to try to triple the energy efficiency with which ethylene, and it's one of our more efficiently produced multi-carbon chemicals, can be generated. I'll talk today about the intensity measured by the partial current density with which these chemicals are being produced. But in the last year, in 2020, we have made major dent on this one, and you can see we're now producing, relative to our target of 700 milliamps, we're now producing with quite high productivity. And then there is a very interesting challenge, very scientifically interesting kind of material science and chemical challenge and chemical engineering challenge, which is to understand what limits reliability today and increase it by a couple of orders of magnitude. The fact that you see here that we're far from spec is actually an indication that we haven't even characterized these for thousands and tens of thousands of hours, because the community is still working to get the basic performance, the energy efficiency figured out and improved. So let me then now start to connect into the role of nano. What's the role of nanomaterials? Well, clearly nanomaterials offer an incredibly diverse range of atomic binding sites, edges and facets and planes. And I'll go over here to one of my nanoparticles, and you can see the different atoms that are being displayed, but you can also see some rows of atoms that are all lined up and of the same type. There are vertices. So there's sharpness, there's compositional variation, there's atoms in different oxidation states. And nanotechnology is just the perfect platform to think about how we engineer chemical reactivity at the interface between a solid, the nanomaterial, and a liquid or a gas, so the electrolyte or the gaseous environment in which we're performing the electrochemical reduction action. And what we're doing with these catalysts is to lower kinetic barriers to moving from an initial to a final state. And so it's a really powerful platform, but as you'll see here, we don't completely understand our own platform fully yet. So our models of catalysts and the environments in which they operate, specifically as it relates to electrochemical CO2 reduction, there's been quite a longer history of work on thermocatalysis, but really intense activity on electroreduction towards multi-carbon products is a little more recent. There's a lot of great science, mechanistic understanding to be developed, as well as there being a lot of really great materials science, so material synthesis to be done, as well as some great engineering to be done. So I'm going to tell a couple of stories. I think all my stories are actually from this calendar year, and I'll be a little brisk here for reasons of time, but perhaps since I'll be sure to leave enough time for questions, we could dive into some of these in more detail if people had questions. So I'm going to start with a bit of a discussion of how our group has recently turned to machine learning to seek catalysts with higher performance faster, essentially to accelerate discovery. And I guess I'll be a little brisk in mentioning some really beautiful pioneering work by Professor Cao-Tang Din. One reason to be brisk is that Professor Cao is presenting, I believe, in the panel right after, so you can ask him to tell you about this too. This is work that he did before he was a faculty member at Queen's. And Cao was first author of a really impactful and now very highly cited paper in Science, building a platform for doing CO2 reduction with gas phase CO2, contacting a liquid electrolyte and putting right at the interface between the liquid and the gas, the solid electrocatalyst. This has been the platform that we've built on in much of the work that I'm now going to talk about. So one of the areas that we've pursued is to ask, how can we make CO2 to ethylene catalysts that have higher Faraday efficiencies? And one degree of freedom at our disposal is to go from the copper catalyst that was the basis of Cao's science paper, and that is the basis of a lot of CO2 reduction work, and see if we can make binary catalysts such as aluminum copper or copper indium or copper tin. And do computational screening initially to see if there's some particularly promising bimetallic materials. And so we screen both for carbon monoxide adsorption. So you can imagine carbon monoxide adsorption driving, can you pile up a nice layer of carbon monoxides that are ready to be coupled with each other to make a 2-carbon product? So there's a reductive step where they form a carbon-carbon bond. Obviously, they need to be close to each other. You need a pretty dense packing of the COs. So you want to control the binding energy of the CO, but also the hydrogen adsorption energy. You want to think about that because, in fact, you're trying to avoid all competing reactions. And if you mostly do H2 production, hydrogen production, you're going to be doing it at the cost to CO2 reduction. So you want to look at both of these. Now, when you envision these materials consisting of copper and something, and the something there's a lot of options in the periodic table, and then you envision all of the planes, all of the facets, all of the vertices that are possible, you actually have a huge chemical space, and you have a huge computational problem. And doing it all with density functional theory from scratch will be very, very demanding. You can easily imagine needing to do 230,000 adsorption calculations on the various surfaces and the intermetallic crystals. So we took a different approach. We teamed up with a great machine learning team at Carnegie Mellon, led by Professor Zach Ulisi. And Zach's team figured out how they could do 4,000 DFT calculations, not 230,000, but then train up an ML model. And then once it was sufficiently trained up and accurate, use the ML model to predict the performance of all 230,000 sites. And of course, checking along the way that it was effective. So then we were able to really screen the chemical space and look for promising materials. And when we did that, we did find copper aluminum and a particular ratio of copper aluminum sites to be particularly promising for having the right combination of CO adsorption and hydrogen adsorption to achieve a very promising looking efficiency through these surrogates towards CO2 reduction to ethylene. So we built it. This is where the nanomaterial synthesis comes in. We actually build a copper aluminum alloy. Then we de-alloyed it. So we annealed it such that it partially phase segregated into a nanoscale mixture of copper-rich and aluminum-rich subphases. And then we etched. You can selectively etch the aluminum out. And so we created little pores, but the etch wasn't so complete that all the aluminum was gone. There was an aluminum-doped copper surface right at the surface of these pores. So through the kind of magic of nanotechnology, now we have a nanostructured material, which is good for high surface area, lots of interaction with the chemistry that we're doing. And it's got a controllable ratio of aluminum to copper right at that surface. And the surface, of course, is the catalytically active site. And so in this study, we were able to achieve consistently a 75% ethylene Faraday efficiency, and in hero devices, an 80% ethylene Faraday efficiency using what we call de-alloyed copper aluminum. So the next direction, I mentioned that activity is a very important priority. And in this work, we were pursuing the goal, sorry, I think I just lost my display. We were pursuing the goal of increasing really the amount of interaction between the input chemicals, the CO2, and the electrons provided by the catalyst. And so, I mentioned some of Cal's pioneering work from a couple of years before in 2018. What he had found was that it was so crucial to bring CO2 from the gas phase, which is shown on the left in this cartoon, into contact with the catalyst where there is also electrolyte, so building this three-phase boundary. But one of the challenges that happens is then if you're going to try to increase the effective surface area here, you will eventually run into the problem of the CO2 as it penetrates the liquid phase being transported all the way to a nanostructured catalyst surface. There's a competing process where the CO2 can form carbonate, which is then very hard to reduce. And so you'll start to lose the ability to further increase your current because of that effect. And so what we saw in this follow-on work that came out early this year was a means to kind of wick the CO2 through a dedicated material whose purpose was CO2 transport. So that's this green shaded material that I show here. And we would put this CO2 wicking or accelerating material right along the surface of the catalyst so that the CO2 could be transported deep into the electrolyte material, and therefore increase the surface area of truly active CO2 supplied catalyst. So the specific approach that we adopted here was to use PFSA, Nafion, which is familiar to many who know a bit about fuel cells and membranes. And we coated our insulating substrate, PTFE, first with catalyst for providing the active sites and also providing electrical conduction. But then around that, we coated this ionomer whose function was CO2 transport. So you can see that now, as shown with the black arrows, there's an avenue towards the transport of the CO2 to where it's needed, penetrating deep into the solution. The result of this is that while previous reports of CO2 reduction to ethylene had been limited to a few hundred milliamps, so 0.2, 0.3 amps per square centimeter on this vertical plot, this team managed to achieve about an amp or a bit above an amp of CO2 reduction per square centimeter. So a major increase in the activity or the partial current density in these devices. Now, at the same time, this work and some of the other work that we've done, they do also point to another challenge that absolutely has to be overcome. This record intensity of activity and this record performance in achieving CO2 reduction, so the record Faraday efficiency, they were done in a very basic or alkaline electrolyte. And in that electrolyte, as I mentioned earlier, there's this competing process where CO2 can form carbonate, which is then very hard to reduce. And so it leads to a loss of the CO2, so incomplete utilization of the CO2. So you can imagine when you're operating one of these plants and you're paying your CO2 bill for the month, you're buying more CO2 than you would like to have to. So it's increasing your costs. And so there's much interest in seeing whether it could be possible to do these same reactions just as efficiently, but without relying on the potassium hydroxide, so the very high pH alkali solutions that have been relied on in some of these early studies. And so our group asked, could you move to neutral media instead of alkaline? And could we sort of find the degrees of freedom in the catalyst design that would permit us to do that? So for this work, again, we turned to theory initially, and we asked some questions about how does this CO-CO coupling process occur? And the starting recognition is that there are two different motifs of binding of CO to the catalyst. One is called a top, the other called bridge. And so the bridge, you can see the two components kind of stuck down together on the catalyst. And what we found through computational work is that it was actually preferable to have a fairly even mixture of these two binding motifs for the CO contacting the catalyst, and that it was when we had one in the bridge, one in the top, that you could minimize the kinetic barrier to the CO2 reduction process. And we then asked, from a molecular standpoint, what could one do to design molecules that would poise the CO molecules, the CO adsorbates or intermediates, in such a way as to tune the ratio among these two motifs, the bridge and the top. And for this, we approached Jonas Peters and Theo Agapi. They're both faculty members at Caltech in chemistry. And Theo and Jonas have tremendous experience in molecular design and molecular synthesis, and also in electrochemistry and in electrocatalysis. So they designed a library of molecules that we could electrodimerize or electrodeposit onto our catalyst. And in this library, they systematically tuned the electron donating and accepting groups. And so they tuned the electron density on their nitrogen centers. And as a result, they tuned the electron donating capacity of the molecules. And this we had hypothesized and done some computational work to show could potentially tune the ratio of a top to bridge. And so with Raman spectroscopy, as shown in panel B, we showed that when we tuned the Bader charge of the various molecules in the library, we tuned the ratio of a top to bridge over the range of interest from sub-half to well over half. And then through electrochemical measurements, we showed that we could achieve essentially a volcano-like behavior as shown in the top left for the Faraday efficiency as it related to the measured atop bridge ratio, which of course then corresponds also to the tuned Bader charge in this molecular layer on top of our catalyst. And so with this, we managed to achieve a 72% Faraday efficiency to ethylene in neutral media. So this was a record for neutral media electrocatalysis at high current density. And it was a route to achieving high productivity and high electron utilization in a neutral environment that avoids this carbonate formation issue. This comes with many benefits. One of them is it's much more readily operated in a stable configuration. So again, building from both the fuel cells and the water splitting electrolyzers, we were able to put this into an MEA, a membrane electrode assembly architecture, and operate over an extended period of about 200 hours in this study with consistent current and consistent Faraday efficiency, thanks to the ability to operate under neutral conditions. I'll say just a bit before I go to questions. Looks like I've got a few minutes before I wrap and we do the Q&A. So I'll just give you a bit of a sense of some of the directions our group is proceeding in now. So one idea is that instead of capturing CO2 from our industrial flue, which is typically done by actually putting it into a liquid and then desorbing it from the liquid and then capturing the gas and then feeding the gas into our system and putting it into another liquid. Another idea is whether you could use that capture liquid and you could directly reduce the CO2 that's captured inside the capture liquid for the production of reduced carbon products. So a year ago, we did this with carbonate, which is one of the capture liquids that's used, and showed that we could make syngas, which is a mixture of hydrogen and carbon monoxide, in one of these systems. So it's instead of a two-stage system, it's a one-stage system, but it's also one where you can fully utilize the CO2 that you've captured. And then, and this is unpublished work, though it's coming out quite soon, we also took amines. Liquid amines provide another route to CO2 capture, and we're able to utilize these capture liquids as well, and the complexes that the amines and the CO2 form together in order to do CO2 reduction to carbon monoxide as well. So that's one interesting direction for this field, which is to integrate the CO2 capture and the CO2 utilization processes. Another direction, and here I'll be brief, is just to perform things not just on the reductive side, but also on the oxidative side. So ethylene oxide is another very big business, and to produce it from ethylene is actually done today with quite a high carbon footprint. But so we've been working on using electrolyzers where the reductive side could be used to make ethylene, as I described, and where the oxidative side could be used to very selectively attach the needed oxygen to make a valuable product like ethylene oxide, or also ethylene glycol and some other work. And then I guess as my last brief story, I'll say that we're also very interested in scale. You can tell that the performance of these technologies is not all done. It's not fully baked. There's more work to do on energy efficiency, carbon utilization. But nevertheless, we believe that seeking to scale and finding what happens and finding the challenges that emerge when you do that is worthwhile. So we're participating in the Carbon XPrize right as we speak. And here we've gone from lab scale, kind of the size of a Rubik's Cube, to a skid that's maybe the size of a reasonable sized SUV, that's going from gram a day to 100 kilogram per day scale. So about 5 orders of magnitude in scale. So with that, I'd love to hear your questions or your comments or have a discussion, but I will just acknowledge the supporters of the work, and I'll acknowledge the members of the group, all of them, but also I've got a few arrows to some of the folks who were particularly helpful in developing this set of slides for today's presentation, so thank you.
Thank you so much for your presentation, Dr. Sargent. The first question that we have is, what is the outlook for the green energy industry? Is it well funded enough and on the right path to solving our energy problems? And what challenges do you foresee?
Yeah, well, I think as you can tell, I'm very excited about it personally, but I think the question kind of hints at two areas that need joint investment. So it would be nice if all we had to do is sort of scale existing technologies that have been proven at the small scale and deploy them. But I think it's more honest to acknowledge that there are scientific questions around new green energy technologies, such as next generation storage technologies, that are not fully resolved. So an example would be the development of the physical and chemical models of how these catalysts that I spoke about today can selectively achieve CO2 reduction to a single valuable product. A single value product is very important, because if you don't do that, if you end up with a cocktail, you end up spending a lot of your money and energy on separation of the products. So there is basic science to be done. At the same time, as you can also tell, I'm a great proponent of doing the applied science in parallel with the basic science rather than in series. And so I think there's much interesting work to be done on systems engineering and on scale and on field testing and on pilot plants, on having things fail in the pilot plants and seeing where they break and doing failure analysis and designing next generation systems, working with industry to adapt existing membranes towards these new products that we're making. So I would say, in answer to the broader question about the green energy sector, I'm optimistic about the outlook, but I would emphasize the need for patient capital. Even the engineering parts of these problems will take time, and it does take investment. I think it's something where industry can and is investing, but it's so big and it takes such a sustained investment, and the benefit is so broad to the population of the world as we seek to address our climate crisis, that it also involves major government investment in order to put in place the patient capital that's required.
Thank you. Our next question is, how does the chemical value of the electrochemical CO₂ conversion compare to that of the same processes found in nature, like in plants and bacteria?
Well, that's a great question. And in general, the concept that there's much to learn from how photosynthesis proceeds is an excellent concept. And in fact, a group of us, like a large group of us, recently got together, I think about 20 of us, and published a bit of a perspective. This is something that came out recently in Nature Reviews Materials on what increased insights has basic science derived from the study of photosynthesis, including all of its various steps, some of which are dark, some of which are light, and how can those potentially be translated to the CO2 reduction field. So, in terms of the value of the products, the product value is typically of the same order in these reactions, but there are some steps that are done in existing biological systems in an incredibly efficient way. And so the overpotential price that is paid to do these upgrades is, in some of the steps done in biology, much lower, much more efficient, i.e., you pay very close to the thermodynamic value of the product in the energy utilized rather than paying extra, which is what this overpotential is that I'm referring to. So one of the opportunities for the, if you like, artificial or nanomaterials-based catalysis community is to learn from biological systems about the design rules of catalytic sites that allow you to achieve a reductive step at as close to what is thermodynamically possible as you can do. And biological systems so far have, in certain cases, in certain chemical transformations, done that better than what we've been able to do in some of the really important chemical transformations for CO2 reduction, such as what I was talking about today.
Thank you. We have lots of questions coming in, so I was trying to filter through them. Let's see. What kind of free parameters would one typically find in the DFT analysis before the ML algorithm runs? Will this not affect the ML results?
Yeah, so the kind of degrees of freedom that we play with when we do the underlying DFT studies is that we kind of initially coarsely position the atoms where they, they're likely to form the different possible facetings, or, an aluminum-rich site here on copper, or a copper-rich site here on a kind of bed of aluminum. And then we relax the structure. So we actually use the DFT to essentially relax the structure down to its thermodynamic minimum, So this is something that has the most negative formation energy possible. So it's a surface that's actually going to exist in nature. So we don't sort of assume as our endpoint for calculation structures that will not exist. We first relax them and ensure that they are actual structures. And then we move from there in order to calculate each of the steps along the pathway towards the formation of and these are multi-step processes, multi-electron processes, towards the formation of the reduced product. And so we explore this large chemical space of surfaces and sort of conformations of atoms and surfaces. And with the binary materials, we explore the different ratios of the two constituents of the bimetallic materials. But then we generate a set of quite computationally expensive calculation results from the DFT. And then through the machine learning approach, we seek to, in effect, we're sort of finding correlations, or we're finding features, such as who are your nearest neighbors? What is the constitution of your nearest neighbor? How far are they apart from you? What oxidation state are you in, and what oxidation state are your nearest neighbors in? So we seek to find these features or these surrogates that end up being descriptors of the binding energies.
All right. Our next question is from a PhD candidate working on perovskites. And he's been working closely following your work, and he was wondering what your opinion is on commercial viability of optoelectronic devices based on it. And can you kindly shed light on where do you see them in the next 10 years?
Yeah, and first of all, I'll say it's a great question. And I'll also just say that I had been originally thinking today I might talk about both the electrolyzer work, which I'm very excited about, and our perovskite and quantum dot work, and then made a last-minute decision that I probably should pick one thing and try to do a reasonable job on it. But I'm very happy that you're interested in perovskites. I am too. In fact, that and the quantum dots constitute about half of what our research group does. So it's a great area to be working in. And it's in solar electricity that it's shown particular rapid progress. It's kind of amazing, actually, what the perovskite community has done in terms of getting to solar power conversion efficiencies, but from this liquid processed, room temperature made material that's a thin film, that's half a micron or micron thick, compared to silicon solar cells that require such high temperatures and that have benefited from decades and decades and decades of gradual performance improvements in manufacturing. So it's amazing how fast the perovskites have moved. They've now achieved approximate parity with silicon, and we're working at both integrating them onto silicon to make solar cells that are better than silicon cells. And we're also making some tandem perovskite cells that have the potential to be better than single junction silicon cells. So clearly the potential is great. The low-cost manufacturing and the low-cost materials are very attractive. One of the key challenges, and I'm sure my question asker is very aware of this, is that the stability of the perovskite devices is not as we would like it to be. Now, what's incredible is that when that was first realized a couple of years ago, again, the material science and the chemistry and the physics and the engineering communities dove into that, tried to understand the reasons why, tried to see what was kind of limiting the stability of these materials, and has made huge progress. And so this year in 2020, including over the last couple of months, people have continued to report advances in stabilizing the perovskite solar cells. And I certainly see no evidence of saturation in that progress. So it seems like the community is continuing to move ahead on this crucial issue to do with material stability, but at least for the moment is moving ahead at a very impressive pace.
All right, I think we have time for maybe one or two more questions, maybe. The next one is, how important is the role of scalable methods for the synthesis of nanoparticles and catalysts? Is this currently a bottleneck for the commercialization of renewable energy technologies?
I think it's a really important issue. Yeah, the scalable synthesis of nanomaterials and catalysts. I guess where it comes to my mind first is in some of the optoelectronic technologies that I was briefly mentioning in response to the perovskite question. One of the more interesting materials for perovskite LEDs, light emitting diodes, and also for generalized nanomaterials-based light sensors or photodetectors is based on quantum dots. So these are semiconductor nanoparticles, a few nanometers in size, synthesized in solution, processed from solution. And they've started to have impact in photodetectors, so in image sensors, in displays, both as color converters, light to light, but also as electroluminescent materials. So they've moved fast, but now we're really getting to the need to scale. Like you can imagine a large area display, there's a real urgent need in order to scale to large areas. There's a lot of quantum dots that are going to be implicated in a 56-inch display. So we need to figure out how to scale the synthesis and simultaneously do it in a way that preserves the monodispersity, so the sameness of each of the quantum dots when you've got billions and billions and billions of quantum dots. So I think, you know, if the person asking the question is working on sort of strategies to preserve excellent optoelectronic properties and ensemble properties, so population properties in semiconductor nanoparticle synthesis as you go to scale, I think it's a continuing, very important challenge that really engages the talents of the multidisciplinary nanomaterials community.
Okay, well, I would like to thank you very much again from all of us for answering all our questions so well and putting together this presentation, Dr. Sargent. With that, I think I'm going to go to Ryan to help introduce the next panel. So thanks again.
Thank you. Appreciate it. Have fun.
Yeah, thank you.